Imagine for a moment being able to, say, tune up your car or fix a leaky pipe, maybe untangle a complex spreadsheet, all without actually stopping what you're doing.
Yeah, no pulling over, no shutting off the main valve.
Exactly. No hitting save and quit, just seamless, almost invisible upkeep. It sounds pretty ideal, right?
It does.
Well, today on the deep dive, we're plunging into a concept that promises just that in the world of manufacturing: opportunistic maintenance. OM for short.
Right.
It's about performing vital upkeep, not by disrupting your flow, but by seizing those, hidden moments right there in plain sight.
Mm-hmm.
Our mission today is to unlock the incredible yet surprisingly untapped potential of OM. We're going to clarify what this concept truly means, explore why it's been around for like over half a century, but remains largely underutilized.
Which is kind of amazing when you think about it.
It is. And then, here's the game changer. We'll reveal how cutting-edge technology, specifically artificial intelligence, is finally making its full impact possible.
That's right. We'll show you how the academic understanding of OM has been, well, fragmented into two very different ways of thinking, and how this study we're looking at unites them.
Okay.
Then we'll dive into a real-world manufacturing application where AI isn't just theorizing about these opportunities, it's actively predicting them and really changing the game for factory floors.
A classic idea meeting new tech.
Exactly. It's a fascinating intersection.
So let's kick things off. Where did this concept even come from? Opportunistic maintenance? You said it's been around a while.
It really has. The core idea first surfaced in the literature way, way back in 1963.
Wow,
Oh,
okay.
the initial goal was pretty straightforward.
Right.
Combine corrective maintenance, that's fixing things when they break, with preventive maintenance, or PM, the routine upkeep.
Right.
The simple but powerful aim was to reduce setup costs and, critically, cut down on total system downtime. At its heart, OM is about performing maintenance whenever there's a, quote, favorable system circumstance.
A favorable circumstance. So an idea from the early 60s seems like a brilliant way to boost efficiency. Yet, you don't hear about it dominating every factory floor. What happened? Why the unmet promise?
Yeah, that's a crucial question this research really digs into. Despite its theoretical benefits and this long history, OM remains surprisingly underutilized in manufacturing.
Still seen as new.
Often, yeah. It's perceived as a new, maybe niche idea, and its underlying theory and the tools to implement it just haven't reached their full potential. This study points to two major bottlenecks.
Okay, what were those?
First, a conceptual gap. There's been this persistent lack of clear, consistent definitions for OM.
Ah.
I mean, think about it. If researchers and industry professionals can't even agree on what something truly means, it's incredibly difficult to standardize it, apply it, or even study it properly.
Yeah, everyone's talking about slightly different things.
Exactly. The literature has really struggled to land on a shared understanding.
Makes sense. And the second bottleneck.
That would be the methodological gap. There's a notable shortage of methods that actually use real operational data. Most existing approaches rely on these rigid, rule-based models, often making simplifying assumptions. And these aren't widely validated by real-world empirical data or adopted in practice.
So, great in theory, but not proven on the messy factory floor.
Precisely. It's one thing to show something works in a perfect theoretical model. It's quite another to prove it with the, chaotic realities of a live production line.
That makes perfect sense. If you lack clarity and practical tools, progress just grinds to a halt, doesn't it?
It really does.
So for you, the listener, whether you're in manufacturing or managing any complex system, why does this matter? What's really at stake here?
Well, the stakes are quite high. OM represents a valuable, largely untapped source of productivity gains.
Okay.
By seizing these opportunities, manufacturing firms can execute preventative maintenance during running production.
While things are still moving.
Yes. This frees up precious time otherwise spent on forcefully stopping machines or dedicating whole shifts just to maintenance. Imagine getting critical upkeep done without hitting the pause button on your output.
That's huge.
It's not just about small tweaks. It's about unlocking significant systemic efficiency.
So if the original concept was so broad, how did experts actually try to implement it back then? You mentioned two different ways of thinking.
Right. They kind of fell into two camps, which this research calls the component view and the flow view. And their understanding of what an opportunity actually is differs quite a bit.
Okay, let's break this down. The component view first.
Sure. The component view is the classic, maybe the most intuitive interpretation. When one component fails, needing corrective maintenance, that unscheduled downtime suddenly becomes
Yeah, opportunity
an
for.
opportunity to perform preventive maintenance on other non-failed components in the same system, while the machine is already down anyway.
Ah, makes sense.
The timing principle here is entirely dictated by these random component failures.
So if a production line stops because, say, a pump failed, you might as well use that unplanned stop to check the valves or inspect the conveyor belts since everything's already halted.
Exactly. This works because of a few things. Economic dependencies, like saving on setup costs because you're already there. Stochastic dependencies, where one failure might affect the likelihood of others.
Yep.
And structural dependencies, where fixing one part physically gives you access to others.
Okay.
Historically, this approach relied on complex mathematical analysis and simulations, all aimed at reducing overall system downtime and costs.
But even with this logical approach, I imagine there were real-world hitches, right? What made it so difficult to actually do this consistently?
Oh, absolutely. There were significant hurdles. First, major component failures are actually increasingly rare in today's high-reliability systems.
Things just don't break as often.
Right. Machines are built better, and predictive maintenance helps avoid those catastrophic breakdowns. So the opportunity from failure simply doesn't pop up often enough.
Okay, scarcity of opportunity. What else?
Second, PM tasks often take longer than the corrective maintenance fix itself. And under pressure to get production back online, crews naturally focus on the immediate breakdown. Adding extra PM can just prolong the outage people are trying to end.
Yeah, you can see that happening. Just fix the main problem.
Exactly. And third, planning is a nightmare. It's hard enough to predict when a failure might occur, let alone which PM tasks would be suitable at that random moment. This makes preparing the work, allocating resources, getting spare parts ready, extremely challenging.
Got it. So the classic view has some serious practical limitations. If your machines aren't breaking down often, where do you find your opportunities? That brings us to the flow view, which the study describes as a new frontier for productivity.
Yes, the flow view is definitely the emerging interpretation. Instead of waiting for something to break, it focuses on maintenance opportunity windows, or MOWs.
MOW.
These are hidden time periods during running production where PM can actually be done without affecting system throughput. The timing principle here isn't failure. It's determined by factors like the contents of intermediate buffers between machines or just natural machine idle times within the production flow itself.
Interesting. So how do these MOWs actually appear during active production? Are they forced or do they just
It,
happen?
it can be both, actually. They occur in two main ways. First, there's the active MOW or AMOW.
Active.
This is when you strategically, intentionally shut down a machine for PM, but you do it while preserving the overall product flow by carefully using those intermediate buffers.
Yeah.
You're creating a window because you know the system can handle it without a hiccup downstream.
It's okay. Planned opportunism.
Kind of, yeah. Second, and perhaps even more interesting, is the passive MOW or PMOW.
Passive.
This is when PM is conducted simply because machines are naturally blocked or starved due to the inherent variability in the system.
Blocked or starved,
Meaning a machine has finished its work but can't pass it on because the next machine isn't ready, blocked, or it's ready to work but hasn't received parts from the previous machine yet. Starved.
okay. Those little pauses that just happen.
Exactly.
Mm.
This happens organically in any complex manufacturing system. A brief pause here, a slight slowdown there. It's just the natural, sometimes chaotic rhythm of production.
And what are these MOWs like? Are they long windows or just quick bursts?
They're typically pretty short term, often ranging from around, say, 5 to 15 minutes.
Not very long.
No. But crucially, they are high frequency. They can occur multiple times every single day, or even multiple times during each production run for a given machine.
Frequent short bursts.
Precisely, which makes them ideal for short-duration PM tasks, especially those known as autonomous maintenance tasks.
What are those?
Those are often performed by the operators themselves. Things like cleaning, lubrication, basic inspection, tightening bolts, the quick routine tasks that keep machines healthy day to day and help avoid bigger problems down the line.
Okay, so perfect for those quick checks and tweaks. And the payoff for actually catching and using these brief, frequent opportunities.
It can be quite significant.
Mm.
Executing these small tasks during MOWs can yield measurable benefits. Throughput gains, maybe 5–10%, reduced overtime for maintenance staff, and potentially increased equipment lifespan because things are kept in better shape.
That 5–10% throughput gain sounds impressive just from using existing idle time.
It is. This approach is particularly advantageous if a company needs to meet excess throughput demands using its existing production capacity.
Yeah.
You're not stopping the line, you're just utilizing these natural lulls that were previously just wasted time.
It sounds incredibly promising, almost like finding free money or free time. But I'm guessing there are still practical challenges to actually doing this, right? It can't be that easy.
No, you're right. There are hurdles. For the active MOWs, the strategic shutdowns, their effectiveness is often limited by the push for minimal buffers in lean manufacturing. If you have very few buffers, there are fewer opportunities to shut down a machine without impacting the overall flow.
Lean works against it sometimes.
In that specific case, potentially. And for both types, active and passive MOWs, predicting them in complex, real-time systems has been historically incredibly difficult. How do you know when that 10-minute window is about to open up?
Yeah.
And then, executing tasks precisely within these very short windows demands skilled, alert operators who can recognize the opportunity, grab their tools, do the task, and finish before the window closes.
High pressure requires quick action.
Definitely.
Okay. So we have these two views, the component view focusing on breakdowns, maybe less relevant now, and the flow view finding these tiny natural pauses, which sounds great but hard to predict. The research makes a strong case that this split, this fragmentation between the views has actually held OM back.
That's a key argument, yes.
That's why the study aimed to create a unified definition. Okay, let's unpack this new definition. What does it say?
Right, the study proposes this powerful, unified definition of OM. It goes like this. The execution of preventive maintenance tasks during opportunities, i.e. limited time periods or system circumstances, during running production when the unit is or do not need to be operational, thereby gaining the equivalent time of the maintenance action for potential production.
Okay, that's quite comprehensive. So it explicitly covers, well, multiple ways these opportunities can arise.
Exactly. It highlights three main sources. First, from idling due to inherent system variability or disruption. That's our passive MOW, the natural pauses.
Got it.
Second, by choice, where you intentionally shut down a unit while maintaining product flow. That's the active MOW.
Right.
And third, from failure, combining corrective maintenance on a broken component with preventative maintenance on non-failed ones. That's the classic component view, still included.
So it brings everything under one umbrella.
Precisely. This definition really unifies the whole concept.
What's fascinating here, reading through this, is how central the concept of time is to this unified view. The study introduces 4 distinct time constructs that help us understand and apply OM more effectively.
Yes, these 4 dimensions of time are really crucial. They help both scholars and practitioners to better pinpoint and ultimately utilize these opportunities.
Okay, what are they?
First, there's frequency. Pretty simple. How often do opportunities occur? For instance, in their case study, they found about 85 relevant MOWs per machine per day.
Wow, 85 times a day.
Yeah, lots of chances. Then there's duration. How long do these opportunities last? In their real-world case, it was typically between 10 and 17 minutes.
Okay, frequency and duration.
Third is sequence. This refers to the temporal ordering of events that dictate when an opportunity might arise, like a machine transitioning from a busy state to an idle state. It's about the pattern of events.
The pattern leading up to it.
Exactly. And finally, timing. This is the precise moment an opportunity begins. An opportunity is predicted to start for machine 5 at 1:25 p.m.
That specificity is key. Understanding these time constructs helps pinpoint and use these opportunities more effectively. But, as we discussed, predicting these subtle short-term windows in complex, real-time manufacturing environments has been the major stumbling block. This is where AI truly changes the game, isn't it?
This is absolutely the study's central thesis. AI can predict these elusive opportunities. It effectively converts what was once considered unpredictable system variability into predictable variability.
Turning noise into a signal.
You could say that. It directly challenges that long-held belief that OM opportunities, especially these short, high-frequency MOWs, are practically impossible to foresee in real time.
That's a huge shift in thinking. Tell us about the real-world application they demonstrated. Where did they test this?
They conducted a case study at a major Swedish automaker, focusing specifically on an automotive engine block manufacturing line.
Engine blocks. Okay.
Yeah.
Complex process.
Highly automated, yes. It involved 32 computer numerical control, or CNC, machines, plus 5 large material handling gantries moving the blocks between machines. A complex, high-value production flow.
And what specific problem were they trying to solve for this company?
Well, the company typically stopped the entire production line for 1 full day every single week just for preventive maintenance.
A whole
A
day.
whole day, mostly for those short tasks, cleaning, lubrication, inspection, each maybe taking only 5 to 10 minutes per machine. They desperately wanted to free up this dedicated PM time for actual production.
Makes sense.
To do that, they needed a reliable way to predict future MOWs for each machine so operators could perform those quick tasks during normal running hours.
And why was AI the perfect tool for this particular problem? Why couldn't a simpler method, like, statistical process control or something, work?
Well, AI was uniquely suited for a few key reasons. First, the sheer high frequency of potential MOWs, remember, dozens per machine per day, happening across all machines.
Too many to track manually.
Way too many. Second, high dimensionality. Predicting an MOW for one machine isn't just about that machine. It depends on the dynamic patterns of the entire production flow, including complex interactions upstream and downstream.
Everything affects everything else.
Pretty much. And third, the need for continuous updating. Conditions on the factory floor change constantly. Predictions needed to be made in real time, adapting on the fly. AI, especially machine learning, excels at learning and adapting to these kinds of complex dynamic patterns from data in a way traditional rule-based models just can't.
Okay, so AI was the way to go. How exactly did they get the AI to see these hidden windows in, I imagine, mountains of raw production data?
They used a pretty clever technique called the hopping windows mechanism. They took 2 years of raw operational event log data.
2 years, wow.
Yeah, millions and millions of state changes from all the machines and gantries. They structured this data into overlapping hopping windows. Imagine a 10-minute window of time. And then they shift that window forward by just 1 minute, creating another 10-minute window, and so on. Lots of overlap.
Got it. Sliding windows.
Exactly. Yeah. The AI's job was then to classify each of these 10-minute windows as either being a maintenance opportunity window, MOW or not, based on whether the relevant units were active or inactive within that specific window.
So it's pattern recognition on these time slices.
Essentially, yes. It allowed the AI to look for patterns in the flow's natural pauses over time across the entire system.
And what did their initial look at this massive data set reveal? Did they actually confirm that enough free time existed to make this whole effort worthwhile?
They absolutely did. Their initial exploration confirmed there was significant amounts of naturally occurring free time hidden in the production schedule.
How much?
The opportunities typically range from 10 to 17 minutes long, collectively representing about 10% of the overall production time.
10%? That's substantial.
It is. And crucially, they found that average of 85 relevant MOWs per machine per day, but they were occurring pretty randomly.
So the potential was there, but it was unpredictable.
Exactly. This initial insight strongly validated the need for AI. It confirmed these opportunities existed in abundance, but they were too random and complex for humans or simple rules to predict reliably.
Okay, so they had the data, they structured it with hopping windows. What AI model did they actually use? And crucially, how well did it perform?
They used a long short-term memory, or LSTM, algorithm.
LSTM, that's a type of neural network.
It is a type of recurrent neural network. LSTMs are particularly good at handling dynamic systems and capturing temporal dependencies patterns over time, which is perfect for a production line.
Makes sense.
Each machine and gantry in the line had its own LSTM model. Importantly, each model was trained not just on its own history, but also incorporating data from its immediate upstream and downstream neighbors to capture those flow dynamics.
Okay, so it considered the context. When they put this AI model to the test against the real data, what did the results show? Did it actually work significantly better than, say, just guessing?
Oh, much better. If we connect this to the bigger picture, the LSTM model significantly outperformed a simple, naive benchmark they set up.
What was the naive benchmark?
It basically just assumed that if the last 10-minute window was an MOW, the next one probably would be too. A very simple persistence forecast.
Right, a basic baseline.
Exactly. The LSTM model achieved an average precision of about 57% and a recall of over 92%. This resulted in an F1 score, which balances precision and recall, of just over 70%.
70% F1 score. How did that compare to the simple guess?
The naive model's F1 score was down around 14.6%. So a huge improvement.
Wow, okay, so it's definitely not perfect. 57% precision means some false alarms, but 92% recall means it caught almost all the actual opportunities, and the overall F1 score shows it's way, way better than the baseline.
Precisely. It's a massive leap in capability. While performance did vary a bit across different machines. Well, for example, machines earlier in the production flow tended to be easier to predict than the material handling gantries or machines later in the flow, likely due to greater interdependencies accumulating downstream.
More complex interactions further down the line.
Seems likely. And yes, there were some false positives predicting an MOW when one didn't actually occur. But the key thing is, the model still identified enough true positives to meet the firm's target number of usable MOWs per shift. It clearly demonstrated the practical feasibility.
That's the bottom line. So, what's the practical outcome of all this? How does this AI actually help on the factory floor day to day, not just in a research paper?
Oh, the trained AI can provide real-time MOW predictions directly to the operators, maybe on a tablet or a screen at their station. This fundamentally augments human decision-making.
It gives them foresight.
Exactly. Instead of guessing or just reacting, operators can receive a precise forecast, something like alert. Machine 1, Machine 32, and Gantry 5 are predicted to have an MOW from 19.48.0 to 19.58.0.
Actionable information.
Right. With this information, the operator, maybe coordinating with maintenance, can then decide whether to utilize that specific 10-minute window for a quick autonomous maintenance task.
Yeah.
It's about empowering the human workforce with intelligence derived directly from the system's own data.
Transforming what felt random into something manageable and predictable.
That's the goal.
This truly feels like a profound development using AI to unlock hidden capacity. So, zooming out now, what does all this mean for you, the listener? Whether you're deep in manufacturing or maybe just trying to optimize any complex system.
Yeah, I think there are a few key practical takeaways here. First, this deep dive hopefully offers a clearer, more unified understanding of what opportunistic maintenance actually is. It gives you a structured framework to maybe recognize and apply its principles in your own settings, moving beyond that historical confusion.
Clarity is the first step. And second, it fundamentally shifts how we should think about downtime or idle time, doesn't it?
It absolutely does.
Yeah.
The study empirically demonstrates that significant free time suitable for maintenance naturally occurs within production systems, especially for those quick, routine tasks.
It's already there, just hidden.
Exactly. It shifts our focus away from relying on idealized theoretical models and towards leveraging real-world operational data to find these hidden pockets of efficiency. It's about finding productivity in the subtle, natural rhythms of operations, not just during forced pauses or breakdowns.
So this research isn't just about tweaking an existing process. You mentioned earlier it signals maybe a more profound shift in overall maintenance strategy.
I think it does.
Yeah.
It signals a potential move toward what the researchers call flow-based maintenance concepts in manufacturing. The idea is that instead of just having suppliers monitor their individual machines in isolation,
Right.
the manufacturer themselves takes on the role of orchestrating system-level maintenance across the entire production flow, integrating information from all parts.
A more holistic view.
Very much so. This could even change how companies think about make or buy decisions for maintenance services. It potentially positions manufacturers more as integrators, combining specialist supplier expertise with this high-level flow orchestration capability driven by data and AI.
That's a huge potential shift in roles and responsibilities. So looking ahead, what's next? What future possibilities and maybe challenges does this research open up?
Well, on the possibilities side, we can certainly expect more research exploring how to integrate AI even further. Maybe using things like reinforcement learning to not just predict, but also automatically schedule PM tasks during MOWs.
Smarter scheduling.
Right, or combining different data types, maybe real-time sensor data, historical maintenance records to enhance the predictions, perhaps allowing for longer PM tasks, or integrating OM with other advanced policies like condition-based maintenance. The potential for a truly intelligent, adaptive maintenance system is vast.
The tech potential seems huge. But with all this advanced tech, there's always that human element to consider, especially when it comes to actually implementing it on the floor.
Yeah.
What do you see as the biggest challenge there?
You've hit on it. I think the biggest challenge moving forward will be resolving the real-world implementation issues. How do you actually design these AI tools so that operators trust the prediction?
ST.
Absolutely. And how do they easily act on them in those short time windows? How do you minimize the cry wolf problem? Too many false positives, leading operators to eventually just ignore the AI's suggestions.
Yeah, alert fatigue.
Exactly. This is where the human element building trust, ensuring usability, designing effective human-AI collaboration becomes absolutely paramount. The technology is clearly advancing rapidly, but integrating it effectively and seamlessly with human decision-making and workflows is probably the next big hurdle to overcome.
Fascinating. So, to recap, we've taken a deep dive into the unified concept of opportunistic maintenance, moving past the old fragmented views. And we've seen how artificial intelligence can act as a powerful key, unlocking those previously unpredictable idle times and turning them into predictable, usable windows for boosting productivity in manufacturing. It's really about finding value in the moments we used to overlook.
Well said. It's leveraging the system's own behavior.
Indeed. And that brings us to our final thought. Think about your own complex systems. Maybe it's your work project flow, supply chain logistics, software deployment cycles, or even managing large-scale events. Where are the hidden opportunities, those micro windows of apparent idle time that you might be overlooking? How could observing patterns, leveraging data, and perhaps even AI down the line help you pinpoint those fleeting moments to optimize your process? Not just when things break or stop, but within the natural rhythm of how things operate. The principles of OM, revealed and amplified by AI, really challenge all of us, I think, to look for productivity in some very unexpected places.